guys, and welcome back to Matthew Wisder for another video. Today we're going to be balancing chemical equations, which is not like my regular Algebra 2 videos, but this topic still involves math. So if you have any questions, write them down in the comments, and I hope you enjoy. But before understanding how to balance chemical equations, we first have to know the law of conservation of mass, which states that matter cannot be created or destroyed in a closed system. It can only change form, meaning the total mass of reactants before a chemical reaction must equal the total mass of products afterwards. For example, when a substance melts or evaporates, the substance form might change, but the amount of matter and the number of particles remain constant. So when we're balancing chemical equations, we can see if the law of conservation of mass is being followed if the number of atoms in the reactants is equal to the number of atoms in the products. So in this first problem, we have phosphorus and oxygen as our reactants and our products. In the reactant side, we have 4 phosphorus and 2 oxygen, and on the product side, we have 2 phosphorus and 3 oxygen. On the product side, we have 2 phosphorus, and if we multiply it by 2, we can get 4 phosphorus, which is on the reactant side. So now we can write down the coefficient of 2 that we use to get the 4 phosphorus on the outside. And now we have a balanced phosphorus on the reactants and the product side. However, since 2 is a coefficient, it's also going to be multiplied to the oxygen, meaning we have to do 3 times 2, which is going to give us 6. Now we have 6 oxygen on the product side. But in order to get the 6 on the reactant side, we also have to do 2 times 3, which is going to give us 6. So we write down that coefficient of 3 that we used to multiply the oxygen on the outside. So now we have a balanced oxygen of 6 on both the reactants and the product side. And once again, the reason why this works is because now the coefficient of 3 is going to be multiplied to the 2 oxygen, which is going to give us 6. In this next one, we have sodium, fluorine, and bromine for our reactants and our products. Now I'm going to put a 1 on each of the elements that are by themselves because there's still an invisible 1 there. When we count, on the reactant side we have 1 sodium, 1 fluorine, and 2 bromine. And on the product side we have 1 sodium, 2 fluorine, and 1 bromine. So far the sodium on both sides are balanced, but the fluorine aren't. I have 2 fluorine on the product side and 1 fluorine on the reactant side. If I were to multiply 2 to the 1 fluorine on the reactant side, then the fluorine will be balanced on both sides. When I multiply by 2 to the fluorine in the reactant side, I have to include that 2 as a coefficient, so that it shows that I'm multiplying the 2 times the 1 fluorine. However, sodium is also there, meaning I also have to distribute that 2 to the sodium. So now it's no longer 1 sodium on the reactant side, because now I'm multiplying it by 2. So now I have 2 sodium on the reactant side, and I still have 1 sodium on the product side. So it's no longer balanced. But in order to achieve that balance, once again, I can just multiply 2 to the 1 sodium on the product side in order to get 2. So I just include the coefficient of 2 on the outside, and now I have 2 of sodium and then 2 of bromine. So that means I also have to multiply the coefficient of 2 to the bromine. So now it's 1 times 2, giving me 2. Which is also the same as the 2 bromine on the reactant side. So now they're balanced. But as you can see, I still have some empty spaces outside of the bromine and outside of the fluorine. So since they're already balanced, I can just multiply it by 1 or put a coefficient of 1 in order for it to stay the same. So I just do 2 times 1, which is going to give me 2 for bromine, and I just include a coefficient of 1 outside of bromine, because it's already balanced on its own. And now I do the same thing for the fluorine on the product side. I just multiply it by 1 to the fluorine, and I include that as a coefficient outside of the 2 fluorine. The reason I use the coefficient of 1 is because on the reactant side, bromine already appears as bromine with a subscript of 2, which contains 2 bromine atoms. This already matches the 2 bromine atoms on the product side, so there was no need to use a coefficient greater than 1.